Hello everyone, welcome to Codynamics. In this video, we are going to see how to set up a case in OpenFOAM for external flow. We are going to do a 3D case using kEpsilon turbulence model, and it is going to be a transient case, so we are going to use the solver pimpleFoam. I have already made a video on snappy hex mesh, so I am going to proceed with a mesh which I have already made, and I'm just going to explain the case setup. So if you have not watched the snappy hex mesh video already, I will give the link in the description. You can check it out. Okay, now let's see what mesh I have already. By the way, this case is just a generic case, so it doesn't mean that you have to use only this type of geometry for this kind of simulation. No, it's not like that. You can use any geometry and do similar kind of external flow, and it will just work fine. Now let's see the mesh. You can see that we have a rectangular box and we have four patches. So let's see one by one. First, we have something called the drone. So this is actually not a drone, but I just named it as drone. Let's see it as face with edges. Okay. Now then we have our inlet. So this is our inlet. Okay, let me hide this so you can see the drone with surface edges. Yeah, so this is the drone. It's kind of a bullet, but I named it as drone. We have our inlet, and then we have our outlet, which is this, and then we have these walls surrounding it, but I just put them into the group of symmetry. So if you see the symmetry group, I have put all the walls into symmetry, so it's not slip, it's not no slip, it's just symmetry. Okay, and you can use slip also, it doesn't matter, it's up to you. If you go to the wall group, you can see only the drone will be there because it's going to be no slip. Okay, this is the mesh which we are going to work with. Now let's take a section and see what we have. I'm going to go to Z normal, hide triangle, light the slice, hide show plane. Then I'll go to Z plane. Let's see with the edges. Okay, this is a okayish mesh, not a very great mesh, not a decent mesh. It's just okayish mesh where you can learn how to run a simulation. So that's why I told you you have to watch the SnappyX mesh video to understand how to make a better mesh for external flows. I'll also try to make another SnappyX mesh video exclusively for external aerodynamics, but as of now you can just follow that video. I'll give the link in the description. Okay, now we have the drone, then we have some refinement up to some region, and then we have the mesh. Okay, now you don't have to worry about this mesh. I have given all the necessary files like the block mesh dict, the snapx mesh dict, the surface feature extract, the mesh quality dict, and I will also give the file, the bullet.stl file. This is the actual stl file which is converted to drone. You can check the snapx mesh file and understand it. I'll give all of these as a GitHub link. You can download and use it for your reference. Now let's get into the actual case setup. I will first open the control dict, which is the most important file. And you can see that we are using the pimpleFoam solver. The end time is 0.1 seconds. The initial delta t is 1e minus 3 and the right interval is 0.001 seconds. Note that I have kept the right control as adjustable, which means for every 0.001 seconds there will be one output file which will be written, which we can use in ParaView for post processing. And I have turned the purge right to 0, so we will retain all the animation files. The maximum current number I have kept as 0.9 and turned on the adjust time step, so we can run adaptive time step. I have included this Q so that you can get the Q criterion just in case if you want. It's very popular in terms of external aerodynamics. This video is not focused on external aerodynamics as such, it's just external flow, but if you want to do it, you can just include the function Q. You will get the Q criterion surfaces formed automatically. And I will also make a video on how to post process this Q, how to generate it, but for simplicity you can check the video of mine called the propeller tutorial where I have mentioned how to post process this Q surfaces. I will give the link in the description, you can check it out. Okay, the control dictator is done. And if we take FV schemes and FV solution, first FV schemes, we are using the Euler scheme for DDT and Gauss linear for almost everything. For turbulence, we are using again Gauss upwind, and for velocity and phi, we use Gauss linear upwind grad U. And for interpolation scheme, it's linear, and grad scheme's limited character is 0.33, and Laplacian scheme character is also 0.33. You can play around the values based on the physics which you are working with. Then for FV solution, I have taken the maximum iter as 50 for P characters, and for P the relative tolerance is 0.01. You can reduce it if you want. And for pimple, I have just changed some of the values. I took the n outer characters as 5 and n characters as 2 and n orthogonal characters as 1 and the relaxation factor as 0.7. So this value I have taken just for simplicity, so that the simulation will just run fine. But if you want more accurate results, you have to work on the mesh, you have to work on these values and check whether your every time step is converging properly or not, and play with these values. Okay, then the next thing is decompose predict. I have 8 cores, so I have taken 8. You can check the number of cores by opening your task manager. Go to CPU in the second tab and see how many number of cores you have. I have 8 cores, so I have taken as 8, and the method I'm using as Scotch because that's my favorite. Okay, now let's go to this turbulence properties. If you go here, you can see that we are using RANS model. So our RANS model is kEpsilon. I will also try to make a video on k omega SST, but it's very simple. You can just understand any tutorial which uses k omega SST and you'll be able to understand. The simulation type you have to mention as RAS instead of RANS, but still it's just RANS. And I have kept the turbulences on and the print coefficients as on. And coming to transport properties, I took the nu, which is the kinematic viscosity, as 1e minus 6, which is in a way air. So you can choose whatever fluid you want. Okay, that's it about these two files under constant. You go to 0, you will have 5 files: the velocity, pressure, the turbulence, kinematic viscosity, and the k and the epsilon. So you can open it and see. So I have taken velocity as minus 50 meters per second in y direction. So if you remember from the mesh, the flow is towards the negative y direction. So let me just quickly open it up. Yeah, if you see here, we can see that the inlet is here, the bullet is here, or the drone is here. So the flow is going to be in negative y direction, right? So that's what we are trying to do in the velocity file. I'm giving negative 50 meters per second because that will be in the turbulent regime. You can calculate the Reynolds number. For drone, it's going to be the wall. So I took fixed value 000. You can also use this no slip. It means the same, but whatever you prefer, you can just go with it. And the outlet is going to be zero gradient in velocity. Walls I took as symmetry in all the files. You can just check all the walls are just symmetry. Okay, there is no change in that. Now coming to pressure, since we already defined the velocity for the drone and the inlet, we will just put zero gradient for those two. But for you, we put the outlet as zero gradient, so we have to define in the pressure, and we are taking it as uniform zero. You can check here. So it's kinematic pressure, not total pressure. Mind that. So that's why we are taking zero pressure at the outlet. Okay. And coming to K, and we took the internal field as 0.06. You can actually calculate it for your case. And the inlet is fixed value internal field, the outlet is inlet outlet, again internal field for both inlet value and out and the value. For drone, again it's a wall, so it's kqr wall function. Coming to epsilon, the uniform 0.0495 is the internal field, so I took inlet fixed value, outlet internal field, and the drone is a wall, so it's epsilon wall function. Then coming to nu t, we have the wall, which is the drone, so it's a nu t u Spalding wall function. The internal field is uniform, very low number, so it doesn't matter what low number it is. You can also take 1e minus 6, or probably even less than that. So you can just take 1e minus 5, that's fine. And for inlet, it's going to be calculated. Outlet is also calculated. That's the convention for nu t. So I hope the boundary files are clear. If you are just going to use the walls also as instead of symmetry, if you are going to use slip, okay, let's say you are just going to use this as slip or no slip, then for pressure you can use the same as what you are using for drone, because both are walls. So you can basically use the same boundary condition. Again, here you can use the kqr wall function. For epsilon you can use the epsilon wall function, and nu t you can use for walls the nu t use Spalding wall function if you are changing the type as no slip or slip instead of symmetry. Okay, so that's it for all the files which we had to look. Okay, now we can go to our terminal. Okay, and we can decompose the case. So that's going to be the first thing. By the way, you have to understand that I already have the mesh in my polymesh folder. So I assume that you already have the mesh. If you don't know how to make the mesh, please check the SnappyX mesh video. It will definitely clear all your doubts. Okay, once we decompose the case, we'll have these folders here, the processor folders. So each processor will take some amount of mesh. While using Scotch, it will try to keep the same number of cells. You can see here, it's all around 82,000, 83,000, 81,000, somewhere around that only. So it will try to keep almost the same number of cells. Then what we have to do is run pimpleFoam in parallel. So MP run NP8 because I have 8 number of cores. If you have more or less, you have to change it in the decompose pardect as well and here as well. Then pimpleFoam parallel, hit enter and just wait for your simulation to end. Now I don't have enough computational resources for this simulation to end because my laptop will overheat and I don't have the time to wait for it. But if you just let it run for enough duration and wait for the files to be written at every 0.001 seconds, then you will have enough animation files which you can do post-processing later in ParaView. I'll also try to make a video on how to do the post-processing for such simulation soon, and I will give the link in the description as well, so you can check it out. Right now you can see that the delta t is 5e minus 7. Current number is less than 1, which is good because the maximum current number we have set to 0.9. It's not crossing that. That's a good sign. And the time right now is 2.3 e minus 6. So now it's 2.8 e minus 6 and it's well under control. But what you have to understand is for every, we gave 5 outer characters. So for every 5 outer characters, this has to reach convergence somewhat. So at least if it reaches around minus 5, e minus 5, something like that, then it's a good sign. Otherwise you might have to increase more characters or more non-orthogonal characters or outer characters. So all that you have to adjust based on the mesh you have, based on the physics you are working with, and try to keep your simulation running properly. If your current number just blows up, check whether your time step is correct, whether you have to refine the mesh or you have to uh, increase the quality. So you have to check all that and then understand why your current number is blowing up. For this case, I think the simulation will just run fine without any problem. It's just matter of time that it will take so much time and then end to give any significant result, probably like end at 0.1, maybe after 1 day, 1 whole day or 2 days. But it depends on your system, your requirements, whether you have the time to wait or not. So I'm going to end this video right here, and maybe with the coarser mesh I will tell you how to do the post processing in another video. So if you enjoy the video so far, if you think you learned something, consider dropping a like, consider subscribing to the channel. If you think your peers will be benefiting from such tutorials, please share it to them as well. It will be of a great help to me. I also have a basic OpenFOAM beginner course on Udemy. I'll give the link in the description. If you are interested, you can check it out. See you in another video. Thank you.